Hi everyone. My name is Eric, and today I'll be presenting my work on adaptive LoRa merging for domain incremental learning. So this is something I worked on together with Julio, who is here, and Luigi Quarantiello and Vincenzo Lomonaco. So the basic idea behind this is, the use of these large pre-trained models. So, out of the box, these models are, usually pretty good in terms of performance on several generic tasks. But when you want to have these models work on um, some specific downstream task, you have to fine-tune these models. And because of the nature and size of these models and the number of parameters that you have to update in order to fine-tune these models, it begs the question, is there a more efficient way of doing this? And so that's why we usually talk about efficient fine-tuning or parameter efficient fine-tuning. So just to give small context, so with regarding full fine-tuning, you have to update the model's entire parameters, which is costly, it's time consuming. So parameter efficient fine-tuning basically allows you to only update a small subset of the model's original parameters or add um, some trainable parameters in order to fine-tune these models. So in this case, you don't go through the stress and the usual time consumption you have with full fine-tuning, and the performance is usually comparable to full fine-tuning. So now, assuming you have this model that you can fine-tune, what happens when you have you're working in a dynamic environment where you have shifting distributions and also you want to find like a simple method of doing these things. So the first thing we look at is LoRA, which is parameter efficient fine-tuning technique. So LoRA introduces these low rank decomposition matrices. So what you do is usually you update these low rank decomposition matrices. You add these to specific layers in your pre-trained model, and you keep the original weights of your pre-trained model frozen, and you update only these. So doing this, you update just a small fraction of the model's original parameters, and you still, as I said earlier, with LoRa, you're able to get comparable performance um, to your full fine tuning. So now we look at, adapt. So now we can efficiently fine tune our models. So how do we do it in a dynamic environment? So firstly, you do this in a continual learning setting. And so you want to enable your models to learn when you have dynamic distributions that's arrive in a sequence. So you want your model to be able to learn without forgetting previously seen tasks. And in this work, we focused mainly in domain incremental learning. So we try to adapt to different domains, but we have the same set of classes across the different domains. So a simple example would be, as you can see here, like recognizing a cat in like a photo or like a sketch of a cat or painting or different domains, basically. So once we have this idea of trying to learn continually. So what if in this case we have multiple LoRa's trained on different domains, and we want to find a way to combine the knowledge from all these individual domains that we have. So that brings us to model merging. So this is a very interesting idea. You basically combine multiple expert models. So these are models which are fine-tuned on specific tasks, and you're able to get the knowledge from all these expert models into one single model without having to retrain the model again. So you just combine um, these expert models, and you don't have to you don't necessarily have to train the unified model again. So the thing with model merging is you're able to learn in like I was saying, in a dynamic environment, because you can have several different distributions of data arriving in a sequence, and you want to combine all these into one. But one of the things that you usually face is something like over parameterization. So you have or parameter redundancy, basically. You have all these expert models, and you have a lot of redundant parameters that you don't need. So usually these merging algorithms try to address this using a couple of different ways. So for example, Tice merging. It uses like this three-step approach. So the first step is to drop most of the redundant parameters. So in their work, they show that you can actually drop a huge percentage of these redundant parameters. So basically parameters that don't receive any significant updates during fine-tuning, and the model is still able to achieve similar performance as to when you have all your parameters. So they firstly drop these redundant parameters, and then they do a sign election. So basically, they select all the parameters. They select a sign, basically. So they do what we call maximum magnitude for each sign. So then they select the sign which has the maximum total magnitude. So once they have these parameters with a unified sign, they then do like a merging of these parameters. And then you have there. So there is much simpler than ties, although there does random specification. So it randomly drops a huge portion of the model's parameters. And then they rescale it with a scaling term. And then they merge the models. And the last one we have is task arithmetic, which is pretty straightforward. So it works with this idea of task vectors. So task vectors are basically the weight updates that we have here. And then with this, you can basically do a lot of arithmetic operations with the task vector. So you can add specialized knowledge or remove what you don't need, and other interesting operations. So yeah, so now we have a full grasp of model merging. And one thing that we discovered when we were playing around with model merging is it can be a bit chaotic, because usually, and also it depends on the model merging algorithm that you're working at. So for example, if you take an algorithm like ties, you have to select weights or coefficients for merging each. Let's say if you're working with LoRa adapters, you have to select coefficients for merging the individual adapters together. So this coefficient is usually like the influence or the importance of each adapter. And it's very difficult to do manually. It's very hyperparameter sensitive. So if you have to, so given N adapters, you have to manually tweak each weight for each individual adapter, and it takes time, And it's more of a guessing game. If you're lucky, you get it right. If not, then you have to keep trying again. So what we proposed to solve this was this adaptive LoRa merging idea. So the basic idea here is you have multiple domains. As you can see here, you have, so this is, these are samples from PACS, which is a domain incremental or domain adaptation benchmark. So they have these 4 domains, and this is from art painting, I guess. This is sketch, reel, and cartoon. So the idea we had is to train each domain individually with one LoRa adapter, and then we pass it through this, which is our coefficients learner. So the coefficients learner computes the weights for each adapter, which determines the influence of each adapter when you're merging. And then once we have these individual weights, we use these weights to do our merging. So it depends on your merging algorithm that you want to use. So whether you want to use Sketch, you want to use ties or DARE or task arithmetic. And then you have your final merge model. Then you can basically test your on the domains you've seen so far. So the coefficients learner is pretty simple. So here we use so given a set of domains, what we firstly do is we construct this small memory buffer. So the memory buffer is this balanced data set that we have that we select as little as 1 sample per class per domain. We tested up to 10 samples per domain, and the difference wasn't that huge. So you evenly sample from each domain to create this small memory buffer. And then what you try to do is to learn these coefficients by using this small memory buffer. So okay, to keep it short. So firstly, given you have to compute these coefficients for each new adapter you see, because the influence of the coefficients change depending on the variation of the adapters that you have. So you can't use the same coefficient values for adapters 1 and 2 as you do with adapters 1, 2, and 3. So every time we have a new adapter, you have to dynamically learn these coefficients. So for each domain, so at the start, what we do is we firstly get the initial coefficients. So here we have these trainable parameters, and this here is a sigmoid, so it keeps the values within a range of 0 and 1. And we have this bias term, which is a positive bound term, so bias. And we use this to scale the coefficients because the sigmoid keeps it within a range of 0 and 1. And we need to do this mostly because depending on which algorithm you're using, the weights need to be within a certain number range. So for example, something like a linear combination, you want to use a set of coefficients that add up to 1, or something like ties, you need to use higher values. So in our work, so we remove all these hyperparameters that you have to tune manually with the original merging algorithms. And we introduce just this hyperparameter, which is the Bmax. And the Bmax is just used to scale the coefficients. So once we have our initial coefficients, what we do is we get a weighted sum of the adapters, and then we have like a merge adapter. So we multiply each coefficient by the adapter, and then we get one merge adapter. So once we have this merge adapter, we combine the merge adapter with the pre-trained model, and then we pass the inputs through the model, we process the input and we compute the loss, and then we compute the gradient of the loss, basically. So we do this iteratively until we have until it converges, and then we have the coefficients that are ready to be used for the merging process. So we tested in a couple of data sets. And so, for example, there's one sample per class. So just one sample per class per domain in our memory buffer. And so here in these columns, we have, for simplicity, because it's very difficult to manually select the weights for each adapter, what we do is we assign equal weights for simplicity in this case. And so given your benchmark here and your merging algorithm, you use equal weights of 1 for ties or for task arithmetic, or equal weights of 1 for ties or their ties, or 3. So we test with different values. And then what you see is depending on the number you use, the difference with each number is very great. So for example, here you have using equal weights of 1. When you increase it to 3, the value significantly changes. When you increase it to 5, it changes a lot. So the same thing applies to the fixed coefficients and the ties as well. Using equal weights of 1, you have a very high value. When you switch to 3, the value differs a lot. So so with our work, we have just this Bmax term, which is the bias term that scales the coefficients. And so as you can see, like I was saying, certain algorithms will expect numbers within a certain range. And so for example, in task arithmetic with 1, so values that range from 0 to 1, it works really well. And we tried with 3. I mean, the difference is also huge, but then it was very easy starting from 1 to get this kind of performance. So compared to the fixed coefficients, you could try a lot of weight values, and you probably will get it, but it will take a while. So the same goes for ties. Ties in this case with different weight values, so fixed weight values. And we try these, and you can get the correct one, but also it's very easy for you to skip the right values and get the wrong ones. So for ours, here we were able to, so using values that range from 0 to 1, the difference with when you use like a value that's 3 or 5, you can see that the difference isn't that huge. For their ties, it's a much more difficult benchmark. But also for the fixed coefficients, you can tell like when you don't use the right range of values, it differs a lot. But for the merge coefficients, although the values are not high, you can also tell that the difference when you switch the values, or when you're not able to get it right the first time compared to others, is not so huge. So it's the same thing for Office Home as well. We have like similar results there. So one other interesting thing that we realized when we're working with this. So like I was saying, for each at each step, or for each domain that you see, you learn these coefficients. And what you can see here for photo, so photo is the closest thing probably to the training distribution. So every time you see new adapters that are trained on a specific domain, you realize that whenever we compute these coefficients, the ones that are easy to learn are penalized are penalized less. So this in the cartoon or sketch, which is pretty hard to learn, these ones are pretty hard to learn. They are the ones that learn the most, and the ones that are closest to the training distribution are the ones that receive the fewer updates. Yeah, so yeah, as I was saying, so this is an example. This is sketch. This is photo. This is cartoon. This is art painting. So in the end, what we can draw from this is that we can easily have these merging algorithms with these adaptive coefficients um, that allow you to basically combine these adapters in a more efficient way, and also gain insight into which adapters are easier to, or which tasks are easier to learn, which ones are harder to learn. And yes, that's it. So if you have any questions, kindly let me know. And yeah, thank you.
Wonderful. Thank you so much for the great presentation, Eric. Does
Yes, you're
anybody
welcome.
have questions? You can raise your hand, you can unmute yourself and ask directly, whatever you prefer. If not, I can start with one question. So you're saying that for your memory buffer, you pick one sample per domain per class, and you also tried up to 10 without this making much of a difference. Do you think this varies depending on the data set, or how would you decide the size of your memory buffer?
Yeah, so when we started this work, we were using about 4 or 5 different data sets. So we used Office Home, VLCS, PAX, Sphero. And what we realized is that it doesn't really matter um, the data sets that we are using. It's just much easier to learn this way because you already have your fine-tuned adapters, and you just combine the coefficients with the outputs of the adapters, and you just try to update the coefficients with that. So it's not um, it is not a very complex task to learn. So if you have like just 5 samples per class, it's also very easy as compared to one sample per class per domain.
Okay, that makes sense. Another thing is that you can see from these weights at the end how different the other domains are from your initial domain, right? So, have you in some way quantified like these differences between these different domains, or is this just an insight that you got at the end?
Yeah, so this was like an unexpected insight. So this is not something that we were looking for initially, but it's something that we came about at the end. So we realized that some domains are much harder to learn, and which is true also if you compare the results in the table, and you check the coefficients that we get. So these are insights that we unexpected insights that we got, and as to quantify that, I don't know. Yeah,
I know that's very interesting. That's why I'm asking you.
yeah.
Hey, does anybody else have questions? Well, if not, then thank you again, Eric, for presenting your work. And we will move on to our second speaker of today, who is Wentao Zhang. He's a PhD candidate studying at the Sun Yat-sen University, focusing on continual learning, fusion learning, and medical image analysis. His research has been published in prestigious journals and conferences such as TMM, Pattern Recognition, MICAI, etc. And he's a member of the open source organization DataWell, contributing to the advancement of AI with a focus on bridging research and practical applications. So with that, I will head over the mic to you.
Okay, I start my presentation. Hello, everyone. I'm Wentao Zhang. I'm honored to be here today to present my work on continual learning. The topic of my talk is parameter efficient fine-tuning for continual learning. In this talk, I will introduce my work from three aspects: research background, excited method, and challenges. Our proposed method. First, a research background, as shown in the figure. When intelligent system is trained by only cards and sheep, it can classify image of cards and sheep. However, when new class, such as birds and fish, are introduced, the system we can accept it to classify all class. But however, old class simple are hard to obtain. As a result, after updating the system, it can classify birds and fish, but fail to recognize cards and sheep. This is phenomenon is known as catastrophic forgetting. And so, how to elevate catastrophic forgetting and achieve continually? There are four major types of continual learning methods. First, recognition-based method. They can constrain parameter update like AWC, Mars. Second, knowledge distillation-based method. This transfers knowledge across tasks such as LWF and ICAR. Third, model expansion-based method, the dynamic expansion architectures like DR and simple DR. Last, pre-trained model-based method, they leverage pre-trained knowledge such as L2P and dual prompt. However, this method suffer from major issues such as Dacier stability dilemma, repeated model growth, relies only on vision information, depends on old class samples. So, to address this issue, we proposed ACL to solve the first two challenges. Then we proposed LangCL to overcome all four challenges. So, ACL is a continual learning framework built up on vision pre-trained models, use adapter for perfect. Key idea of ACL, decomposition class incremental learning into task incremental learning and task ID selection. As shown in this figure, we can find task incremental learning in test time. Task ID is provided, but in class incremental learning, task ID is not available. So in this work with a pre-trained model and adapter-based tuning, task incremental learning can be efficiently achieved. To implement task incremental learning, we designed a vision adapter for CNN backbones. Inspired the transform-based adapters, we designed CNN-based adapters. This adapter is inserted between CNN stage and works a task ahead for efficient task incremental learning. Then, in the training phase, step 1, train adapters and task head. Use current task data and store all the class sample. We leverage OD detection by treat as all the class samples as an others class, helping the adapter better description current task classes from no current classes. Step 2, freeze and store train adapters, then use balanced data across all tasks to fine-tuning task heights. After training, in the inference, step 1, task ID selection based on OD detections. For each test image, we can compute each other's probability across all tasks. We can select the task head in the low or others probability task head. Step 2, within the selected head, we can choose the class in the highest probability as the financial prediction. So to evaluate ACL, we conducted intensive experiments on the 3 data sites: SKIN 8, PAS 60, and CFAR 100. We use mean class recall or as the main evaluation metric. This result shows that ACL consistent opt performers strong baselines or setting, even on the class imbalance SKIN 8. Application studies confirmed each component of the ACL contributes to its overall effectiveness. Under the different pre-trained CNN backbones, the ACL consistent opt performers representation strong baselines. We proposed the adapter-based continual learning framework ACL and introduced a multi-head strategy for efficient training and inference. Empirical results on multiple datasets confirmed ACL effectiveness, and ACL achieves SOTA performance on the multiple datasets. Other work. LangCL is a vision language model-based continual learning framework that doesn't retain all the samples and takes all for challenge. Key idea of the LangCL convert class incremental learning into the task incremental learning, but without task ID selection. The others introduce text modality to guide vision representation learning within a fixed embedding space. To achieve task incremental learning, we use LoRA for efficient vision language model fine-tune. LoRA is inserted into the key and value project layers of the multi-head attention module. Use the image text align to enable language guidance learning of the vision representation. Then we use large language models to generate rich text description for each vision class and construct fixed text OOD anchors to assist vision representation learning. This is different show this process. So during training, we opted with the task-specific vision adapter for image embeddings close to the text anchors will push them away from other class, and finally freeze and store the adapters. In the inference, we integrate text and vision information for inference result inquiry task ID selection. Step 1, contribute how like a test image belongs to any learned class. Step 2, choose the class with the highest and the final prediction. So we evaluate long tail on the CIFAR 100, ImageNet R, and SKI 40. Use ACC MCR for continual learning performance and AOC for OOD detection. The proposed long tail demonstrate excellent continual learning performance even on the class imbalance ImageNet R. And for OOD detection, we consider the learned class as the ID class and the unlearned class as OOD class to evaluate the OOD detection performance of each method. From this result, it can be observed that compared with the baseline method, the proposed long tail also demonstrate excellent OOD detection performance. The application study result confirmed the effectiveness of proposed component. This result demonstrates that even with a large domain gap between pre-training and downstream data, the proposed long tail still shows excellent continual learning performance. This result demonstrates that even under different pre-trained vision language models, the proposed long tail can achieve the strong continual learning performance. Although long tail was proposed under a large small sentence, this result demonstrates that it still achieves strong continual learning performance even in few short scenarios. And for this work, proposed a vision language model-based continual learning framework, long tail, without retain all the data. First, to demonstrate that fixed semantic text space enhance the continual learning. First, to show that fixed text OOD representation improve both continual learning and OOD detections. Long tail achieved SOTA performance on multiple benchmarks. In addition, I have some related papers to comment. That's include my presentation. Thank you.
Wonderful. Thank you so much. That was very, very interesting. I'm gonna open the floor for questions. If not, I would like to start with one question. So, you mentioned this, for instance, that you use the LLMs to create these textual descriptions of the visual classes, and then you have these textual auto-distribution anchors. Could you give some concrete examples of this based on your training data? Like, so I can, what would be like a visual class, how it would be described, and what would be an auto-distribution anchor?
Sorry.
Oh yeah, so I'm just saying, could you give like an example from your training data, like from your data, say how an LLM would describe one of your visual classes?
You can slowly your question. I network is unstable.
Maybe I can let you know which slide I mean. Okay, I'm not seeing the screen anymore. Because basically you use LLMs to extract textual descriptions from the images, right?
Yeah.
Yeah. So what would be, for instance, one of these visual classes in your data that is, and how would it be described?
I understand that your question is text anchor how to guidance image closer.
Yeah, exactly. Like how can I imagine this in the context of a specific data set? Like just an example, just to make it a little bit easier for me to imagine.
So I understand it. I understand it. Because language guidance can use it because this language alignment space, and in the continual learning process without change. So I know per vision class text anchor text anchor is fixed, not change. So we can connection different tasks and compare this result.
Okay, there is one anchor per class. Okay, yeah, that makes sense. Yeah. Okay, any other questions from anybody in the chat?
Sorry. I forgot to turn on my video camera.
Oh, it's turned on now. No worries. Okay, then in that case, if there aren't that many questions, then thank you again to both speakers, and I hope you all have a lovely day. I will see you again on the April seminar.